The very first question that arises in our mind is, what are these elementary particles? And certainly their story starts from the nucleus of an atom. And in this video, I'll be talking about, uh, I'll try to give the general introduction of the elementary particles, I mean, what these elementary particles are. And to start with, what is important here is that the structure and the constituents of atoms that we have, atoms, they have, an atom has a nucleus, it has electrons, it has protons, it has neutrons. And this structure and the constituents of these atoms came to be known by the year of 1932. Nearly it was 1932, when the atom was discovered to contain a positively charged nucleus. And the size of this nucleus of the order of 10 to the power of minus 15 meters, which is 1 Fermi. And having protons and neutrons surrounded by electrons with equal number of protons and electrons. In a neutral atom. And it was followed by the discovery of the other particles. It was followed by the discovery of positron. It was discovered by Anderson from investigating the track of the particles in cloud chamber. We have talked about it. And this cloud chamber acts as the detector, in which these particles were deflected by the magnetic field similar to that of electrons, but with an opposite curvature. So when magnetic field was applied, there happened to have some particles whose curvature was opposite. Now, at the same time, the electromagnetic phenomenon could be explained by the emission of photons. Emission of photons as quantum radiations, and the existence of neutral particles of negligible mass, what's called as neutrinos, and its antiparticle as antineutrino, as postulated by Pauli in 1933. And this could account for the missing energy of the beta particle spectrum. The predictions of neutrinos, they could explain the emission of beta particles, the energy emission of the beta particles, where we could see that beta particles could have all possible energies. And then probably in 1934, it was Fermi who obtained the correct shape of beta spectrum, if we rightly remember the beta spectrum, something like this. Okay, so this is the energy of the beta particles, and this is the number of beta particles that are coming out of radioactive nuclides. And the correct shape of this beta spectrum was given using Pauli's hypothesis of emission of neutrinos and antineutrinos by these radioactive emitters. Now, most of the phenomena in the atomic physics till 1934 could be explained by the discovery of nearly 7 fundamental particles. And if I have to categorize them, it's electron, positron, neutron, proton, gamma ray photon, neutrino, and antineutrino. And all these particles, except this neutron, are stable. They are stable if they are left to themselves, and they will live forever. They will live forever. And in order to account for the stability of nucleus, it was Yukawa who proposed the existence of some short-lived particles named mesons. And which jump back and forth from neutron to proton, and vice versa, and have short mean life with virtual emission and absorption within the nucleus. So that's accounted by Heisenberg's uncertainty principle. Now, accordingly, the mass of such particles should have been between 200 to 300 electron masses, the masses of electrons. However, it was probably in 1935 when Anderson, what he did, he observed the track of the cosmic ray particles with positive charge and a mass in the given range, 200 to 300 masses of electrons. Now, the particle was positive, and it was named mu positive, mu meson. And during the same year which we had, we could detect the negative charge and the comparable mass of these mesons, mu positive mesons and mu negative mesons. And both of these particles had a mass of the order of 207 masses of electron. But since these particles interact very weakly with the nucleons, they could not account for the exchange. They could not account for the exchange nuclear force. And later on, another cosmic ray particle was observed in nuclear emulsion detectors. And it was detected, and it had a mass of nearly 273 masses of electron. And this particle was able to interact. It was able to interact strongly with nucleons and decay into a weakly interacting particle with a mean lifetime of the order of 10 to the power of minus 8 seconds. And this particle was named as pi meson, or pion. And this particle is denoted by pi. Now, what we have three pions. Three pions were discovered during 1937. And it was around from 37 to 1950. And what we have, the positive pion, the negative pion was discovered, and a neutral pion was discovered. And this neutral pion had a mass nearly 264 times mass of electrons. So then there was, in the same range of time, there was the discovery of mu mesons that we have and the pi mesons. And they were followed by the discovery of short-lived heavy mesons. And they were denoted as K plus, K minus, K0, K bar 0, and eta 0. And a number of short-life particles having mass between that of a neutron and deuteron were also observed, and they were described, they were designated, they had their designation as lambda. This is lambda, and some with sigma plus minus sigma 0, and chi minus chi 0, omega. Such particles were observed in the interaction of high energy cosmic rays. And the threshold energy for the production of such particles, probably heavy particles, it lies in the high energy range. And they could be produced and observed in the laboratory using high energy particle accelerators. high energy particle accelerators. All right. Now, whatever I have mentioned here, these particles are basic elementary particles, as they are the basic constituents of the matter. And they have got different characteristic properties. And they are either stable or have longer mean life as compared to the nuclear time scale. Nuclear time scale is very small, and that scale is nearly 10 to the power of minus 23 seconds. And these particles have their corresponding antiparticles with opposite, what anti means is opposite charge and magnetic moment, or magnetic moment, or spin magnetic moment. So they are antiparticles. And construction of ever increasing powerful accelerators, certainly it has led to the discovery of more than 300 elementary particles. More than 300 elementary particles. And these are obviously not truly elementary. They are only elementary than the nucleus. That could be the precise way of putting an exhaust on this, that these are not truly elementary. They are elementary with respect to the nucleus. And most of such particles are massive and complex than nucleons. And they cannot be the fundamental building blocks of the matter. I mean, in particular, they cannot be they cannot be the building blocks of the matter. In particular, the atomic nucleus. And with such a huge number, it was once apparent that we could never, ever come up with some fundamental law that's governing the behavior of these particles. But in recent times, experiments are revealing symmetry, and this symmetry appeared to be consistent with the analysis in terms of relatively smaller number of truly fundamental, elementary, and basic particles. And these fundamental and elementary basic particles are called as quarks, which are really the subnucleonic building blocks. They are the building blocks of nucleus. And the very strong attractive intranuclear force is due to the exchange of gluons. It's due to the exchange of gluons among these quarks that we have. Whereas the repulsive internucleonic forces are chiefly due to electrostatic repulsion. So this is how the race of these elementary particles could be. Some of the particles could be predicted as Dirac predicted the antiparticles of electron as positrons. And to every particle there is an antiparticle, except a few of particles who are antiparticle of themselves, like photons, gravitons, and so on. So after this, we would like to go with the classification of these elementary particles in the next video.